get something here?
Yes. All right. So today the topic is bond types. Bond types is the first topic. We'll get to a couple of other topics. So first of all, we need to define what a chemical bond is. So a chemical bond is when a molecule is formed between two or more atoms, okay? So two or more atoms, two or more atoms connect through electromagnetic, and I'm just going to abbreviate that, oh my goodness, what is going on here? I'm just going to abbreviate that. Electromagnetic forces wow, that O is really low. Forces to make molecules. Okay? So when two or more atoms come together and they are bonded together through electromagnetic forces, they make a molecule. Right? That is a chemical bond. So remember when we talked about physical changes versus chemical changes a couple weeks ago? Chemical changes are when things bond together, when things are changing in their chemical state. They are either bonding together between atoms or they are breaking apart. Okay? I know that is really hard to look at. Sorry.
What's that?
Electromagnetic. Electromagnetic. We're going to talk about that. We talked about ions a bit, and you'll see how electricity and electromagnetic forces and so forth are connected to all of this. Questions on what a chemical bond is so far? Pretty straightforward. It has to do with the electrons. And spoiler alert, everything has to do with the electrons. Okay, I'm going to move on here. If you need to check this out again, of course, just go back and watch the video. Okay, so there are two major types. Two major types of bonds. First, we should talk about, well, first of all, before I get there, does anyone know the two different types of bonds? Something that you may have heard about before. What?
In 6th grade, my science teacher told us about bonds. I don't even know chemicals. There's two different ones. One, she explained it like this: one you can't change back, and one you can.
So I think you're thinking about physical change and chemical change.
Oh,
yeah. With chemical bonds, the two major types are covalent, and another one which we'll talk about in just a second. Covalent bonds. Covalent bonds. So a covalent bond is when the atoms share electrons. I'm going to do the classic parenthesis S because it can be just an electron or it can be multiple electrons from their valence shells. Okay? Yes, and we're going to get to that they cosplay as noble gases, and the reason why they're doing this. So, covalent, that makes sense, right? Co meaning together, valent meaning valence shells. So they're sharing electrons from their valence shells. Before we get to the other type, and I apologize that I have to stand right here, it kind of blocks vision, but if I don't stand here, then people on the video can't hear me. Before we get to the other type of bond, let's look at some examples of covalent bonding. Okay, let's look at a couple of examples of covalent bonding. So I want you to look at your periodic tables. Pull those out or pull one up on good old ptable.com. Okay? And I want you to look at oxygen. So if you have those laminated army ones, you will see numbers in the top corner like this. If you have one of the fold-out ones, the white fold-out ones, you'll see something in this top corner, but it won't look exactly like this. Those actually represent the same thing. They're called the Electron Configuration. So when you look at oxygen, you see this 2 and then this 6. Okay? Now let's look at chlorine, shall we? 2, 8, 7. If we look at antimony, 2, 8, 18, 18, 5. Does anyone have any guesses as to what these numbers represent? You are so close, Miguel. The numbers in this top corner. That is related to the shells, yes. These are the electrons in each shell. And remember that in the valence shell, every atom wants to have 8 in its final shell. Yes. Yes, so antimony has 5 electron shells. And its final shell, which is its valence shell, right? It has 5. It wants 8. So does oxygen. Oxygen has a shell with 2 and a shell with 6. Okay? So when we look at oxygen, it has 6 valence electrons. 6 valence electrons. Okay? How many electrons does it want to have in its valence shell? It wants 8. the number of electrons in each shell. 8, this is the happy golden number.
Why is it unhappy number?
Why is 8 the number? Okay, so I'm not going to get into this because this has to do with quantum chemistry. And this is not only above what this class needs to cover, it's right at the edge of the most advanced chemistry class that I took in college. So I don't want to go there. It's way beyond what we need to cover. What I want you to know is that every atom wants to have 8 valence electrons. And I don't expect you to know why. I just expect you to know that that is the case. Okay? So 8, it wants 8. So we're breathing in and out, yes? What is the atmosphere that we breathe primarily made out of? There's a couple of things that it's made out of. Nitrogen, about 80% nitrogen. And then it's about 19 or so % oxygen. So it's right around, oxygen and nitrogen make up about 99% of the atmosphere that we breathe combined. Both of those are called diatomic molecules, which I'll explain what that means at a different time. But the oxygen that we breathe is not just a single oxygen atom. It is O2. All right? In a chemical formula, and we'll talk about this in much greater detail later, in a chemical formula, you have the atomic symbol, and then you have the number of atoms, which is shown here. So O2, meaning there are 2 oxygens. Okay? Well, the 2 oxygens both have 6 electrons. They want 8, 6 electrons in their outer shell, right? In their valence shell. They both want 8 in their valence shell. So they make a deal. Okay? The 2 oxygen atoms make a deal, and we're going to do this. We're going to draw O and O. And then I'll do red for the nucleus. So there's the nucleus. We'll go back to black for the, let's do, actually. So we have 1 orbital. And that orbital has 2 electrons. Do you see that in your periodic table here? In the top it says 2. Okay, the top it says 2. So the first shell has 2 electrons. We'll use yellow. 1 electron, 2 electrons. 1 electron, 2 electrons. That's the inner shell. But it wants to fill its outer shell, which is this one right here, its valence shell. So pretty. You just have a whole bunch of circles. Remember that this right here is supposed to be an O. I guess I could have typed that out, but whatever. Okay, and in that shell we have 1. Oh, let's change it back to the highlighter. Here we go. 1, 2, 3, 4, 5, 6. All right. And this one, it has the same thing. 1, 2, 3, 4, 5, and 6. Okay? So these two atoms make a deal. They say, I will share 2 of my electrons in my valence shell if you share 2 of yours. That way we can both pretend like we have full valence shells. Okay? So what happens is these two and these two go back and forth between the two atoms. They are shared between the atoms. That way, both of these oxygen atoms can go to Comic-Con dressed up as neon. Remember that they want to be, everybody wants to be a noble gas. And in this case, oxygen is just dying to be neon. Just really wants to be neon. And so these two together pretend that they are both neon by sharing their electrons. Miguel?
Is neon toxic if you breathe it?
No. Neon is non-reactive. In fact, neon has a very similar density to air, and it doesn't have any smell or taste, so you wouldn't even detect it. The only problem would be if it was like the atmosphere that you were breathing was primarily neon. You would die, not because it was toxic, but because you didn't have enough oxygen. Okay? So these two oxygen atoms are pretending to be neon, when they're actually just two oxygens. Okay? So that's covalent bonding. These are sharing electrons. These electrons are covalent. They are valence electrons for two different atoms. And this is specifically called a double covalent. Covalent. That makes sense? Why it would be a double covalent bond? Because there are two electrons being shared. And if, in the case of nitrogen, which nitrogen has 5 electrons in its outermost shell, the nitrogen that we breathe is also N2. There are 2 nitrogen atoms bonded together. Okay? N2 is a triple covalent bond. They are sharing 3 electrons, also pretending to be neon. Franklin?
Like noble gas is not supposed to react, right?
Yeah.
Isn't helium the thing they fill the limits with and like it blew up?
Hydrogen. Hydrogen is what the old Zeppelins were made out of or filled with, and hydrogen is extremely reactive. So if you fill a blimp full of helium, you're good. Helium is not going to react with anything. If you fill a blimp with hydrogen, you are just asking for it to explode. And not only does it explode, it explodes really, really efficiently. The only thing that is made from hydrogen exploding is water. It doesn't even make carbon dioxide or soot or anything else. It just makes pure water.
Wait, so like when that blimp was like burning through the ground,
When the Hindenburg exploded, there was a huge amount of water released in the atmosphere. I mean, huge compared to the atmosphere itself is really small, but yes, it was a lot of water. Many water molecules were formed in that explosion. Fun, yes. Oh, the humanity, as was said. Okay, so that's covalent bonds. Okay? Now let's talk about the other major type of bonding, which is ionic bonds. Ionic bonds are bonds where the atoms are bound together by stealing each other's, sorry that I cannot type today. I can never type though. Let me think about this. It would be each other's with the apostrophe after. Yep. Each other's electrons. So this is not a sharing situation. This is a stealing situation. And you will see how that is different from covalent in just a second. Ionic bonds. What do we know about the first part of this word? What does ion mean? Yes, making the atoms charged. Charged. Okay. These become ions because they steal electrons from each other or give an electron. Well, I don't know about give. What's the word for something that has been stolen from you? What did you do? You were pilfered. You were robbed. Yeah, there you go. You were mugged. Pilfered. You were mugged. Okay? So when we talk about ionic bonds, usually, covalent bonds are usually between two atoms that are on the same side of the periodic table. Covalent bonds are usually between atoms that are on the same side of the periodic table. So for instance, oxygen with itself, right? Or nitrogen with oxygen, or fluorine with chlorine. All right? When we talk about ionic bonds are generally between atoms that are on opposite sides of the periodic table. So for instance, if we look at this here, fluorine and lithium, or sulfur and magnesium. When they're on opposite sides of the periodic table, they make an ionic bond. So let's look at sodium, shall we? How many electrons does sodium have in its valence shell? One. Yes. Everyone's like, is this a trick question? It's one. One electron in its valence shell. Do you think that sodium is particularly happy to have that one electron? It wants 8 in its valence shell. It is 7 electrons away from that. So it is not happy about this. Okay? The easiest way for sodium to get 8 electrons in its valence shell is just give away that shell, that outermost shell. The easiest way for sodium to have 8, it can pretend to be neon if it can simply get rid of that one electron. And the way that it does this is it will bind with chlorine. And chlorine pretends to be argon. Chlorine is just one away. It has 7 valence electrons. It's so close. It really wants that last electron. real bad. Okay? Really wants that last electron. So it's going to do anything possible to get that electron. And the way that it does it is it steals it from sodium. Has anyone heard of sodium chloride before? It's table salt. Okay? It is table salt. Chlorine gas by itself will kill you. Chlorine gas by itself will kill you in a very terrible way, even in small amounts, which is dissolving most of your lung tissue. Okay? Chlorine gas, and you may have heard about the Geneva Peace Accords, the Geneva Compact, or no? Yeah, the Geneva Convention, but there's an actual document that was signed by a bunch of countries after World War I. World War I was the first time that we started using chemical weapons as a species. Chlorine gas was one of those. Chlorine gas was a bad time for everyone. Okay? It was so bad that we thought, you know the saying, all is fair in love and war? Well, we're going to make sure that not everything is fair in love and war. Chlorine gas is not cool. But yeah, but shooting someone with, a piece of metal at high velocity, that's okay. But having them breathing chlorine gas, that's over the line. Okay? It's war, yeah. Okay, but sodium by itself is also really dangerous. Sodium by itself explodes when it touches the air. Okay? Sodium by itself explodes when it touches the air. So here's an idea. How about we take a thing that explodes when it touches the air and a gas that literally melts your lungs, and we put them together, and then we put that on top of our baked potato. And it tastes delicious, right? The whole thing about salt, like when you're making potato chips, I make homemade potato chips at home. I fry up some freshly sliced potato slices. And the thing about potato chips is that they can never have too much salt. Just salt away. Okay, I guess you can, but it's really hard to oversalt chips, let's be honest. Okay?
I get like the lightly salted.
You get the lightly salted because you're a weirdo?
Sometimes
Well, I have just learned that I can no longer trust your judgment, Sheldon. Not that I could afford. No, I'm just kidding. All right. So, fluorine and chlorine and bromine, all of these really want, bromine, bromine and fluorine and chlorine really want one more electron. Do you remember that this is the reason why they are in the same column? The same column has the same number of valence electrons. Okay? Fluorine and chlorine and bromine and iodine all have 7 valence electrons. So when we have let's do a couple of simpler atoms. Let's do fluorine and lithium, so that I don't have to draw so much. Because let's be honest, nobody wants to see me draw that much. So lithium. We have lithium here. Okay? Let's draw the nucleus. The nucleus, and then let's draw the electron orbitals. They were red, right? I don't remember. Electron orbital number 1. And how many electrons does it have in its first orbital? 2. Always 2. Okay? And if we draw, how many electrons does it have in its next orbital? 1. 1 electron. Oh, shoot. 1 electron. Okay? Now let's look at chlorine. Chlorine, Cl. Chlorine has how many shells? Has 3. Oh, wait, let's do our nucleus. Well, that's a really small nucleus, but pretty accurate in terms of size here because of the atomic radius, right? So chlorine has 3. Oh, I was going to do fluorine. Oh, well, we're doing chlorine. 3 electron orbitals. 1, 2, 3. And those electrons are in a configuration of 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Oh, that last electron is really flat. All right, it's squished, okay? Don't judge it. What is going to happen here? What is going to happen with these atoms? Huh? What? They're not going to share. Because does lithium want to share?
No, it wants to steal.
No, lithium doesn't want to steal. Lithium wants to be mugged. Lithium's going and flaunting its electron, being like, hey, look at my electron. Be ashamed if somebody came and stole it from me. Right? Well, yeah. Lithium is finding the, anyway, lithium is just wanting to be robbed, okay? Lithium goes and finds chlorine and gives it its valence electron. Okay? And so now we have and that electron goes over here. Now both atoms are happy because both atoms have full valence shells. And you're thinking, but Mr. Croshaw, lithium only has 2 valence electrons. The first shell only has 2 electrons. And so it cannot hold any more. And so this is a full valence shell. So for lithium, hydrogen, and helium, their valence shell, and same with beryllium, their valence shell that they're trying to have full is just the first one, which only has a spot for 2 electrons. Okay? Remember that we talked about valence shells want to have 8 electrons with a little asterisk, and that asterisk is, except for the first shell, which only has 2. Franklin?
I'm not related, but why is light so good at impacting radiation?
That's a great question. Lead is extremely stable. And it is very difficult to ionize lead.
So it's like giving it an extra proton.
Giving it an extra proton would make it into, where is it? PB would make it into bismuth. Giving it an extra proton, it doesn't really care all that much. Hitting it with high energy particles, it doesn't really care. It just kind of absorbs all of that. It's really stable. Okay. So what has happened here? Electromagnetically, what has happened here? The lithium ion, this lithium atom is now a lithium ion. And what kind of ion has it become? Anyone? What kind of ion has lithium become? Vince? It has become a cation. Wow, that's a terrible C. Cation. And chlorine has become Cl-, which it meaning what? What kind of ion has it become? An anion. Do we see how that works? Two elements that are on opposite sides of the periodic table want to steal each other's electrons or have their electrons stolen in order to fill their valence shell or have a full valence shell. It's not stealing, it's more like donating, I guess you could say, but stealing is easier to remember. So lithium and chlorine get together and lithium says, I really want to be helium. And chlorine says, I really want to be argon. And they say, all right, well, if I give you my last electron, I get to be helium. And if you take it, then you get to be argon. So let's make a deal. And we will do this thing where we become ionized. We become charged by giving each other electrons. Okay? Cool. So this leads us, so two major types of chemical bonds, covalent and ionic. Covalent and ionic. Now, I want you to tell me, so if we had a, let's see here. So when we draw these pictures, and yes, they are absolutely beautiful, I know. Do we really need to draw these inner shells? These inner shells that have all these electrons, do you think those are important to our drawing? Yes, says Ella. Why would they be important? It does. It shows how many electrons, but when we're talking about the bonding, are these electrons in here important at all in how atoms bond together? No, they're not, right? So if we want to do a full electron configuration drawing, then absolutely they're important. Like Ella said, they're still they're electrons, right? We should know how many electrons there are. But when we're talking about bonding, in chemistry, we use something called the Lewis dot structure. Lewis dot structure. And when we look at that, so for instance, let's look at carbon. How many valence electrons does carbon have? V E minus equals, how many valence electrons does it have? It has 4 valence electrons. Whoop, 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 whoop. 4. So carbon really wants 8. So it's kind of in a weird spot. The ionic situation is not a great situation because it would have to give up all 4 of its valence electrons, which is very difficult to do. And a single covalent bond doesn't really make a lot of sense either. And the way that we draw the Lewis dot structure for carbon is we do 1, 2, 3, 4. In the Lewis dot structure, you simply are drawing the valence electrons. Drawing the valence electrons let's make this a little bit smaller. You're drawing the valence electrons around the atomic symbol. Okay? Drawing the valence electrons around the atomic symbol. So carbon has 4. So you draw 4 dots around. Okay? That's carbon. When we are talking about, let's say we're talking about oxygen. The Lewis dot structure of oxygen is 1, 2, 3, 4, 5, 6. And you draw them in 4 quadrants, okay? So you draw them as if it was a box, okay? So we have, in the middle, we have the atomic symbol, which I'm just going to use A. And then we draw the electrons in the quadrants right here. And we just draw those as dots. Electrons go here in the boxes. Okay? The electrons go in the boxes. And so this is annoying, right? Why isn't this symmetrical? That would just make us feel better about it, right? Because humans like symmetry. Do we not? Well, in the Lewis dot structure, you start at the top. You start at the top here. So this is quadrant 1. This is 2. This is 3. And this is 4. So you start at the top and then you go around counterclockwise in the quadrants and fill in the structure. Okay? So carbon is nice and symmetrical because it has 4. Oxygen is not symmetrical. Boron will not be symmetrical. Just get over it, I guess. Because some people would be tempted to draw boron like this. And boron has 3, 1, 2, 3, kind of like a triangle situation. You don't do this. Okay, don't do that. The correct configuration for boron is B in the middle, 1, 2, 3. Okay? So that's Lewis dot structure. It is a much simpler version of doing this, right? In this, we're drawing the nucleus, we're doing each shell, you're filling in the shell. In the Lewis dot structure, it is nice and easy. You just go atomic symbol in the middle, fill in the electrons as dots around there. So when we look at different types of bonds, so let's talk about carbon, shall we? So carbon, one interesting thing about carbon is that it loves to make covalent bonds with other carbon. And the way that we signify carbon bonds is by, or not carbon bonds, the way that we signify covalent bonds is by drawing a line. And it loves to make these covalent bonds with other carbons. Okay? And here we have the Lewis dot structure for carbon in a covalent bond with 4 other carbons. Okay, so this carbon is very happy. The carbon in the middle is very happy because it is pretending to have 8 valence electrons by sharing one of its electrons with each of these other 4. And they are sharing one of theirs with it. Huh? Yeah. So this carbon in the center has 4 valence electrons, and then it is sharing the other 4 here. So it has 1, 2, 3, 4, and then it is sharing 1, 2, 3, 4. So what you could do is you could draw an electron.
So the one in the middle
here.
Shares all of them.
Uh-huh.
And ones to the outside share one.
So the ones on the, so you could draw an electron at each of these points here. See how that works? So this carbon is sharing all 4 of its valence electrons with the other 4 carbons around it, and those 4 carbons are sharing one of their electrons with this one. These carbons are now looking for 4 or 3 other things to bond with. And this actually happens a lot. This would bond to some other things, more specifically hydrogen. So in this case, the hydrogen would come and bond out here to these carbons, and you'd end up with C5H9, which is a type of hydrocarbon, hydrogen carbon. You could burn it, essentially. Okay? So we have covalent bonds with the other carbons. Now, if we look at this, if we look at one of the most common chemicals that we will use, well, that I will use in some demonstrations and so forth, which is methane, which is CH4. So CH4, when we look at that, we have a carbon in the center, and that carbon is bonded with 4 hydrogens. And these hydrogens are actually giving up their 1 electron to become hydrogen ions, hydrogen cations. And we have CH4, where these are all sharing, or not sharing, these are all giving up their 1 electron to the carbon, so the carbon can have 8 electrons. Isn't oxygen flammable? So yes and no. So oxygen is not actually flammable because oxygen is the definition of flammable. So it's like without oxygen, you cannot light anything on fire. Okay? Without oxygen, you cannot light anything on fire. You need something to light on fire in an oxygen environment. Does that make sense? Oxygen will react with other things by those things bursting into flame, but oxygen itself is actually not burning.
So if you're in a room with pure oxygen and you lit a lighter, what do you tell
if you were standing in a room of pure oxygen and you lit a lighter, you would instantly go up in flame.
Why?
Because you are the thing that is reacting with the oxygen. Okay? The oxygen wants to react with other stuff. Okay? It cannot react with itself any more than it already has to be O2. Okay? So it needs something to burn. Okay? All right? So that's Lewis dot structure and chemical bond types. I'm going to end the video here.